In this video, we're going to look at some examples of how we can predict how a radionuclide is most likely to decay. So when you're doing these problems, these are the types of things that you want to consider. So the first thing you want to look at is, what is the atomic number? If the atomic number is greater than 82, we know that there are no stable nuclei. And the most common way that nuclides with atomic number greater than 82 are going to decay is alpha decay. Now, of course, we know from the chart of the nuclides activity that we did that they don't have to decay by alpha decay, but if we were going to make a prediction just based on the mass number and the atomic number, if the atomic number is greater than 82, then our most likely prediction is going to be alpha decay. If the atomic number is less than 82, then what we want to do is calculate the N to Z ratio, or the number of neutrons divided by the number of protons. If we find that the N to Z ratio is too high, then our prediction is going to be that it's beta decay. If we find that the N to Z ratio is too low, then our prediction is going to be that it's either positron emission or electron capture. All right, and these, so on the previous slide, we talked about whether the N to Z ratio was too high or too low. These tell us what the optimal N to Z ratio is going to be for different atomic numbers. As atomic numbers increase, the optimal N to Z ratio gets bigger, and so what we want to do is see which one of these categories the nuclide that we're dealing with falls into, and then we'll know what the optimal N to Z ratios should be. We can compare what the actual N to Z ratio is, and then we'll know if it's too big, it's going to be beta decay. If it's too small, it's going to be positron emission or electron capture. So let's look at a couple examples. All right, so we're told that carbon-14 is radioactive, so we want to know how it will most likely decay. So we've got carbon-14. So you may want to pause these to find these elements on the periodic table, but the atomic number for carbon-14 is Z is equal to 6. So if it has 6 protons, the mass number is 14, so 14 minus 6, the number of neutrons is 8. So when I calculate the N to Z ratio, I get 1.33333. All right, so now I want to look and see which category carbon-14 falls into. And so because the atomic number is 6, right, it falls into this category. And so we're looking for an N to Z ratio of 1. So because this is bigger than 1, the N to Z ratio is too big, and our prediction that this is going to go by beta decay. All right, so now we're given radon-222. So when we go to the periodic table and we find the atomic number for radon is 86. And so now I don't have to even consider the N to Z ratio, because for the radionuclides that are greater than 82, our prediction is that it's going to be alpha decay. All right, now we have platinum-184. So when I go to the periodic table, I see that the atomic number for platinum is 78. So then to get the number of neutrons, 184 minus 78, we have 106 neutrons. So the N to Z ratio I get 1.36. So now I've got to see which category platinum-184 falls into. So the atomic number is 78, so it falls into this category. And then when I see, right, 78 is pretty close to 80, right? So it's not true that if the N to Z ratio is in this range that's stable, what this means is for atomic numbers of 40, we want the N to Z ratio to be close to 125. For atomic numbers close to 80, we want the N to Z ratio to be close to 1.5, right? So because the atomic number is 78, right, that's close to 80, so we're looking for an N to Z ratio that's close to 1.5, so we're obviously smaller than that. So our N to Z ratio in this case is too small, so our prediction would be positron emission or electron capture. All right, finally, we want to do scandium-47. So when I go to the periodic table, the atomic number for scandium is 21. So 47 minus 21, we have 26 neutrons. So my N to Z ratio comes out to be 1.24. So then, all right, my atomic number is 21. So scandium falls into this category. But of course, 21 is on the side closest to 20, right? So we would expect that the N to Z, we want to be pretty close to 1. So the fact that it's 1.24 tells me that it's too big. So this is going to be beta decay.